Something is heating up deep beneath central New Mexico, and a recent sequence of earthquakes has drawn renewed attention to one of North America's most unusual geological features. Around the town of Socorro, a region long known to geologists for its restless underground activity, the earth has once again begun to shake. The tremors are not occurring randomly. They are unfolding directly above a vast body of partially molten rock, hidden approximately 20 miles, or about 32 kilometers, beneath the surface. Known as the Socorro Magma Body, this enormous underground reservoir has fascinated scientists for decades because it represents one of the largest known accumulations of magma beneath the continental United States. The timing of the earthquake swarm raises important questions. Why are earthquakes clustering above this deep magma reservoir? Is the magma body expanding? Is additional molten material rising from greater depths? Or are these tremors simply part of a long-running geological process that has been quietly unfolding for thousands of years? As seismic instruments continue recording movement beneath New Mexico, attention has increasingly focused on whether the Socorro Magma Body represents a dormant volcanic system slowly evolving toward a more active future. Located within the Rio Grande Rift, a vast zone where the North American continent is gradually being stretched apart, Socorro occupies a unique geological setting. The rift extends from Colorado through New Mexico and into northern Mexico. Unlike dramatic plate boundaries such as California's San Andreas Fault, the Rio Grande Rift is a region where deformation occurs more subtly. The stretching process creates fractures within the crust, allowing heat from deeper levels of the Earth to move upward more efficiently. For millions of years, this slow extension has altered the landscape of the American Southwest. Mountains have risen, valleys have subsided, magma has periodically intruded into the crust. While most of these processes occur over immense timescales, the geological activity has never completely ceased. Socorro sits near the center of one of the rift's most remarkable features. During the 20th century, scientists studying seismic waves noticed something unusual beneath the region. Earthquake-generated waves appeared to slow dramatically at a particular depth. Such behavior often indicates the presence of molten or partially molten material because seismic energy travels more slowly through magma than through solid rock. Further investigations confirmed that a large body of partially molten rock existed beneath the area. Over time, increasingly sophisticated measurements revealed the true scale of the feature. The Socorro Magma Body extends across hundreds of square miles and occupies a relatively thin layer sandwiched within the crust. Although it is not a gigantic underground ocean of liquid lava, it contains enough molten material to significantly influence regional geology. One of the most surprising discoveries emerged from satellite observations and ground-based measurements. Scientists found that the land's surface above the magma body was slowly rising. The uplift was subtle, amounting to only fractions of an inch per year, yet it was measurable across a broad region. Such inflation suggested that pressure was accumulating at depth. The process resembled what occurs at many volcanic systems around the world. When magma enters underground reservoirs, the surrounding rocks may expand slightly, producing uplift at the surface. In volcanic regions, increasing inflation sometimes precedes eruptions. However, the situation beneath Socorro appeared more complicated. The uplift had been occurring for decades without any sign of magma reaching the surface. No volcanic vents opened, no lava emerged, no ash clouds appeared. Instead, the crust seemed to be slowly adjusting to persistent pressure deep underground. The recent earthquake swarm adds another layer to this complex picture. Earthquake swarms differ from traditional earthquake sequences. A typical earthquake pattern often involves a major shock, followed by smaller aftershocks. Swarms, by contrast, consist of numerous earthquakes occurring within a relatively short period without a single dominant event. They frequently occur in volcanic regions because moving magma can fracture surrounding rocks and alter underground stresses. When earthquakes begin clustering directly above a known magma reservoir, questions naturally arise regarding the relationship between the two phenomena. The connection between magma and earthquakes is well established. Molten rock exerts pressure on its surroundings. As magma migrates through fractures, it can trigger seismic activity. Even relatively small changes in underground pressure may produce measurable earthquakes. Yet earthquakes can also occur independently of magma movement. Tectonic forces continuously act upon Earth's crust. Faults accumulate stress over time before releasing it through seismic events. Distinguishing between tectonic earthquakes and magma-related earthquakes requires careful analysis of their depth, location, frequency, and seismic characteristics. In Socorro's case, the overlap between the earthquake swarm and the magma body has attracted particular attention because the region already possesses a long history of unusual seismic behavior. The area surrounding Socorro has experienced repeated earthquake swarms over many decades. Numerous studies have documented recurring clusters of small earthquakes concentrated within the rift. These events demonstrate that the crust beneath central New Mexico remains active despite the absence of recent volcanic eruptions. Some earthquakes originate relatively shallow within the crust, others occur at intermediate depths. Together, they reveal a region where geological forces continue reshaping the underground environment. One reason for this activity lies in the presence of heat. Heat fundamentally changes the behavior of rocks. Cold rocks tend to fracture suddenly when stressed. Hot rocks often deform more gradually. In regions where elevated temperatures exist, complex interactions develop between brittle upper crustal rocks and softer, deeper materials. The Socorro Magma Body serves as a major heat source. Even if large portions of the reservoir remain partially solidified, the presence of molten material influences temperatures throughout the surrounding crust. Over long periods, this heat weakens rocks and alters stress patterns. The result is a geological environment particularly prone to persistent seismic activity. Understanding the significance of the earthquake swarm requires examining the magma body's structure. Contrary to popular imagination, underground magma reservoirs are rarely vast chambers filled entirely with liquid rock. Modern geophysical studies reveal more complex systems consisting of crystals, molten material, and solid rock mixed together. The Socorro Magma Body appears to fit this description. Researchers believe much of the reservoir consists of a crystal-rich mush rather than freely flowing magma. Melt is present, but it occupies only part of the total volume. This distinction matters because fully liquid reservoirs behave differently from partially molten systems. A highly molten reservoir can transport magma more efficiently toward the surface. A crystal-rich system often remains stable for extended periods, sometimes hundreds of thousands or even millions of years. The challenge lies in determining whether conditions are changing. Earth's crust is not static. Magma reservoirs evolve continuously. New magma may enter from deeper sources. Existing melt may cool and crystallize. Pressure may increase or decrease. Fractures may develop, creating new pathways for movement. If fresh magma is rising into the Socorro Magma Body, the earthquake swarm might reflect the crust responding to those changes. If no new magma is entering the system, the earthquakes could simply represent ongoing adjustments within the rift environment. Evidence gathered over the years suggests that the reservoir has not remained completely inactive. Measurements of uplift indicate that pressure has persisted beneath the region. The rate may fluctuate over time, but the long-term trend suggests continued geological activity. Some studies have estimated that magma injection at depth could explain portions of the observed deformation. Such findings have fueled speculation regarding the future evolution of the system. The phrase fledgling supervolcano occasionally appears in discussions of the Socorro Magma Body. The term attracts attention because of its association with enormous volcanic eruptions capable of affecting entire continents. Yet understanding what constitutes a supervolcano requires careful consideration. A supervolcano is generally defined by its capacity to produce exceptionally large eruptions involving hundreds of cubic miles or hundreds of cubic kilometers of volcanic material. Such eruptions are extraordinarily rare. The presence of a magma reservoir alone does not automatically qualify a system as a supervolcano. Many regions contain substantial magma accumulations without ever producing eruptions on that scale. At present, there is no evidence indicating that Socorro is preparing for an imminent supereruption. The magma body remains deeply buried. No surface volcanic activity suggests that magma is rapidly approaching the surface. No dramatic changes comparable to those observed before historic eruptions have been documented. Nevertheless, the reservoir's size and persistence make it an important feature worthy of continued monitoring. Geological history provides additional context. Volcanic activity has occurred throughout the Rio Grande Rift over millions of years. Numerous volcanic fields dot New Mexico's landscape. Lava flows, cinder cones, and volcanic deposits testify to a long history of magma generation beneath the region. Some eruptions occurred relatively recently in geological terms. Others are far older. Collectively, they demonstrate that magma has repeatedly found pathways to the surface. The Socorro area itself contains evidence of ancient volcanic processes. These events show that magma has interacted with the crust for extended periods. However, the existence of past volcanism does not necessarily predict future eruptions within any specific time frame. One of the most intriguing aspects of the Socorro Magma Body is its depth. At approximately 20 miles, or 32 kilometers, below the surface, it resides much deeper than many magma reservoirs associated with active volcanoes. Depth creates both opportunities and obstacles. A deep reservoir possesses substantial insulation from surface conditions. It may remain molten for long periods, yet magma seeking to erupt must travel through many miles of crust. Along the way, it encounters cooler rocks, pressure changes, and structural barriers. Many magma intrusions never reach the surface. Instead, they solidify underground, forming plutons that remain hidden until erosion exposes them millions of years later. For an eruption to occur, a sequence of geological conditions must align. Sufficient melt must accumulate, pressure must build, pathways must develop, magma must retain enough buoyancy to continue ascending. The recent earthquake swarm alone does not demonstrate that these conditions are being met. Still, swarms deserve attention because they provide clues about underground processes. Every earthquake acts like a probe, illuminating otherwise inaccessible regions of the crust. By analyzing seismic waves, scientists can infer changes occurring miles below ground. Patterns matter. If earthquakes migrate upward over time, that may indicate magma movement. If they remain concentrated along existing faults, tectonic processes may dominate. If uplift accelerates simultaneously with seismic activity, pressure changes become more likely. The challenge is that geological systems rarely produce simple answers. Earthquake swarms can emerge and disappear without leading to eruptions. Some volcanic systems experience decades of seismic unrest before returning to relative quiet. Others produce eruptions following only brief periods of warning. Each region behaves according to its own geological architecture. In Socorro, decades of monitoring have revealed a system that appears active but patient. The magma body has persisted. Uplift has continued. Earthquakes recur. Yet surface volcanism remains absent. This combination creates uncertainty. The uncertainty is not evidence of impending disaster. Rather, it reflects the inherent complexity of understanding processes occurring many miles underground. Even with modern instruments, direct observation remains impossible. Researchers must reconstruct hidden events from indirect measurements. Advances in technology have significantly improved that effort. Satellite-based radar can detect subtle ground deformation across broad regions. Dense seismic networks record tiny earthquakes once impossible to measure. Improved computational models allow scientists to simulate magma behavior with increasing sophistication. These tools have transformed understanding of the Socorro Magma Body. Earlier generations knew only that something unusual existed beneath central New Mexico. Today, scientists possess detailed images revealing the reservoir's approximate dimensions, depth, and physical properties. Yet important questions remain unresolved. How much melt currently exists within the reservoir? Is the amount increasing or decreasing? What mechanisms sustain long-term uplift? Are fresh magma injections continuing from deeper levels of the mantle? To what extent does the earthquake swarm reflect changes within the magma body itself? The answers carry implications extending beyond New Mexico. Large magma reservoirs represent important laboratories for understanding continental volcanism. Studying them helps researchers learn how magma accumulates, evolves, and sometimes erupts. Insights gained from Socorro may improve understanding of similar systems elsewhere around the world. The region also illustrates a broader truth about Earth's interior. Many people associate volcanic hazards with obvious landmarks, such as towering mountains, steaming craters, or active lava flows. Yet significant geological processes often occur far from such features. Deep underground systems may remain largely invisible while continuing to shape the crust above. Socorro exemplifies this hidden activity. Residents may see no volcano on the horizon, yet a massive magma reservoir lies far below their feet. The recent earthquake swarm serves as a reminder that geological forces remain active even in landscapes that appear stable. Over immense timescales, those forces can transform regions dramatically. Continents stretch and fracture. Magma accumulates and cools. Faults develop and shift. Mountains rise and erode. Processes measured in fractions of an inch annually may eventually reshape entire landscapes. The Rio Grande Rift itself emerged through such gradual change. What appears static during a human lifetime may be dynamic when viewed across millions of years. Current observations suggest that the Socorro Magma Body remains part of that ongoing evolution. The reservoir continues influencing crustal behavior. Earthquakes continue occurring. Heat continues flowing upward from Earth's interior. Whether these processes ultimately lead toward greater volcanic activity remains uncertain. The recent swarm demonstrates that the system is not dormant in the conventional sense. Geological activity is occurring. Energy is being released through earthquakes. Stress is being redistributed within the crust. Yet activity does not automatically equal escalation. Many geological systems experience persistent unrest without progressing toward eruption. The distinction between a restless magma reservoir and an erupting volcanic system is substantial. Crossing that threshold requires specific conditions that may or may not develop. For now, the earthquake swarm highlights the importance of observation rather than prediction. The data indicate movement within an already active geological environment. They confirm that the Socorro region remains one of the most fascinating geophysical locations in North America. They reinforce evidence that a vast magma reservoir continues to occupy the crust beneath central New Mexico. Most importantly, they remind us that Earth's interior remains far more dynamic than surface appearances suggest. Roughly 20 miles, or 32 kilometers beneath New Mexico, heat, pressure, and molten rock continue interacting within a system that has persisted for an extraordinarily long time. The recent earthquakes offer a glimpse into those hidden processes, revealing a landscape still being shaped from below. Whether the Socorro Magma Body represents the earliest stages of a future volcanic center, a long-lived magma reservoir destined never to erupt, or something between those possibilities remains an open question. What is clear is that the region continues to evolve. The earthquake swarm has brought renewed attention to a geological feature that refuses to be ignored, a feature whose immense size, persistent activity, and deep-seated heat ensure that Socorro will remain one of the most closely watched geological regions in the American Southwest for years to come. Another factor contributing to interest in the Socorro region is the unusual way seismic energy behaves there. Over decades of monitoring, researchers have documented a reflective horizon associated with the magma body, a phenomenon rarely observed with such clarity elsewhere in the continental United States. Seismic waves generated by earthquakes often bounce off this zone, allowing scientists to map portions of the structure much as sonar maps features beneath the ocean. These reflections indicate a boundary between rocks with very different physical properties, consistent with the presence of partially molten material. The existence of this reflective layer suggests that the magma body has maintained at least some degree of melt over extended periods. This is significant because magma naturally cools and solidifies with time. To remain partially molten for so long, the system likely receives continued thermal input from deeper sources within the Earth. That does not necessarily mean large quantities of magma are actively rising at present, but it indicates that the heat engine driving the system has not completely shut down. The broader geological setting supports this interpretation. The Rio Grande Rift remains one of the most prominent examples of continental extension in North America. As the crust stretches, faults develop and pathways open through which heat and magma can move upward. The process is gradual, measured not in years or decades, but across millions of years. Yet even slow extension continuously modifies underground stress fields. Those changing stresses may help explain why earthquake swarms repeatedly occur in central New Mexico. Faults that might remain locked in other regions can become periodically reactivated as pressure accumulates and is released. The presence of elevated temperatures further complicates the situation by altering how rocks respond to stress. Instead of producing a single large earthquake, some regions release energy through numerous smaller events spread over days, weeks, or months. Recent activity appears consistent with that pattern. While the swarm has attracted attention because of its location above the Socorro Magma Body, the earthquakes themselves remain relatively modest in size. Their importance lies less in their individual strength and more in what they reveal collectively about ongoing crustal deformation. One possibility is that the earthquakes reflect adjustments occurring within the rocks above the magma body. As pressure slowly changes at depth, the overlying crust may respond through fracturing and fault movement. Another possibility is that small quantities of magma or magma-related fluids are migrating through existing weaknesses. Such movement does not necessarily signal an approaching eruption. In many volcanic and magmatic systems around the world, magma intrudes repeatedly into the crust without ever reaching the surface. The distinction between intrusion and eruption is crucial. Geological records show that most magma generated within Earth never emerges as lava. Instead, it cools underground and becomes part of the crust. Massive granite formations exposed in mountain ranges today often represent ancient magma chambers that solidified before reaching the surface. The same outcome is possible for future magma entering the Socorro system.